Let's discuss the hotel reservation system. Most of the components used in this system can be tweaked a bit and reused to explain systems such as Airbnb, ticket booking system, flight booking system, etc. As most of the components that I will be explaining here can easily be reusable. And this is how system design should be studied as well. Okay, let's see requirement gathering for a hotel reservation system or hotel booking system. We are considering a big hotel chain, say 5K hotels and 1+ million rooms overall. So it's quite a very big and popular hotel chain. Customers can make bookings or reservations. You can call it anything. They can basically make those reservations, edit them, cancel them, etc. and couple of all these functionalities. Then there needs to be an admin panel to CRUD hotel and rooms. So for addition of newer hotels and all these rooms, which we discussed above, that it has 1+ million rooms of different types, then it has too much hotels. It's quite a big chain. So all the CRUD related to that is to be done by admin panel. So we need admin APIs for that. So we need control over that. Hotel price can change and is linked to the type of room user wants to book, availability of rooms in a hotel at a given time. And this is how actual systems behave as well, based on the availability of rooms, specific type of rooms in specific type of hotels. The price keeps on dynamically changing in terms of if the availability is less, it's becoming quite popular on those certain dates, so price shoots up a bit. If it's not that hot dates or active dates, then the price is the usual price. This is what is mentioned as is linked to the type of room user wants to book, availability of rooms in a hotel at a given time. So price also closely relates to inventory of rooms and how much are booked or available. We would eventually need this to maintain the inventory of rooms of these hotels, and then how many rooms have been booked, how many of them are available on some certain dates. So eventually price closely will relate to it. We need to support room reservations in a highly concurrent environment. It can be that there is a festive season going on and a lot of users try to book very limited number of available rooms. So let's say some specific dates are some festive season going on and a lot of users are trying to book the same room. So it's sort of a highly concurrent environment. So we need to handle those scenarios as well, considering we have limited number of availability of rooms at that point of time. Let's see back of envelope estimations. So as we saw above, we took 5K hotels and 1+ million rooms. So we took 5K hotels and 1 million rooms overall. From storage perspective, it's not too much data, as it will be majorly text information and images. We need to focus more on QPS for such systems, which is query per second. Taking rooms are 70% occupancy overall across all hotels, plus average booking, let's say, is of 3 days, which is itself quite a lot. Like having 70% occupancy overall across all hotels and all rooms. So we do 1 million rooms we have, then we have 70% occupancy. And as the average booking is of 3 days, so we do 1 by 3, because one time booking QPS, like query, one time query would come and it would make the room booking, average booking for 3 days. So it becomes 1 by 3. So this comes out to around 240K reservations. What would be the QPS or queries per second? This would be 240 times 1000 divided by 24 into 3600 at a per second granular level, which comes out to be 3 reservations per second. Generally, the flow of users will be users browsing the hotels and then their rooms, picking and finalizing the room to book on certain date range, and then finally booking it. Makes sense? Considering only 10% proceed further till the end of every step, because a lot of users do browsing on a lot of these hotels and then their rooms, but eventually lot of users drop out or something like that, and then considering, let's say 10% proceed further till the end of every step and make that booking over that same browsing flow. So let's see the request per second to checkout. This comes out to be around 30, and RPS to hotel plus room browsing, let's take 10 times of that as 300. So not much of a load on our system per second. So we can eventually see there is not much of a load on our system per second. APIs design. We would need couple of APIs for the hotel browsing first. We need get v1/hotel/id. This gets info about the hotel for that specific hotel ID. Then get v1/hotel/id /room/id. This gets us the info about specific rooms in a specific hotel ID. Then we need couple of APIs to do admin related work like add up hotels, do CRUD on the rooms, do CRUD on the hotels, and so on. So a post call on v1/hotel, this adds a new hotel with the particular payload having that hotel information which we are adding newly. Then put is v1/hotel/id. This is to update info about a particular hotel with this hotel ID. Then we need reservation related APIs. We need get v1/reservations. This gets the reservation history of logged in user. Then we can have get v1/reservation/id. This gets details about a specific reservation for the logged in user based on this reservation ID. Post of v1/reservation, this is when a user makes a new reservation. Delete v1/reservation, this is when the user cancels their reservation. So we can make this call. This can also be a post call as well. To make a reservation, the payload would look something like, it can have couple of fields as I have mentioned here below. We need a start date and end date. This is date range over which we are making the reservation. That is important. We would need hotel ID, which hotel we are making reservation in. Then we need user ID, the particular user making this reservation. Then room ID, which room user is reserving. We can also discuss this in different way, because if you see, generally from hotel's perspective, you don't book a specific room ID. You book from a specific hotel ID perspective and from the start date, end date range, and then you need the user ID. We don't need the room ID. So we can also discuss this in different way, that we give user ability to book on the types of rooms, and based on our inventory, we take the booking. Later on, when user would check into the hotel, they will be allocated the specific room number of the type of room they booked. So this is how actually things work. Like our system will take up the booking for that specific type of room, and when the users would later check into that hotel, they will be allocated to specific room ID or specific room numbers, and the system would be updated by that based on the availability of that specific type of room they wanted to book. Then we need reservation ID. This needs to be unique as it also helps our system in achieving idempotency to prevent double booking over a network delay or something. We have discussed idempotency in a couple of our other systems as well. But yeah, this is quite important. So we'll make a reservation ID as idempotent key. When the user lands on the final checkout page, we can have a reservation ID, say a UUID generated and attached to the specific details over checkout for this particular user and the reservation this user is going to make. So if user tries to make reservation with same checkout details multiple times, maybe due to network lag or delay or something, we validate and avoid double bookings. This idempotency flow has already, as I mentioned above, has been discussed a couple of times in a couple of my other systems as well. Now let's see DB schema, how things would look like, and the entities will be mapped to each other. We saw that from storage perspective, the scale of our system isn't that large, but we need to focus more on reservations journey, avoiding double bookings, maintaining and showing the inventory properly, booking limited rooms even in highly concurrent environment, etc. And a couple of these things we need to focus upon, considering storage is not an issue for us. Considering all of this, along with our system being read heavy as compared to writes, which is write is making an actual booking, being made in read heavy here is that users are browsing across a lot of hotels and then their rooms. And as we saw at the back of envelope estimations, 3 reservations per second was their actual booking being made, and 300 requests per second were coming for the browsing stuff. So a read heavy system as compared to writes being coming in. We can pick for an RDBMS to get its asset guarantees, which is atomicity, consistency, isolation, and durability. So let's see the DB schema. For hotel, we can have hotel ID as the primary key. We can have name of that hotel, location of that specific hotel, and similar other details about the hotel. For user, we can have user ID as its primary key. We can have name of the user, and similarly, to keep things as simple as possible, I have skipped adding too much details about maybe hotel, user, and couple of other entities. But yeah, it will have other details about the user as well. Then for room, we would need room ID as the primary key. We would need the room type ID. We would need price for that room, hotel ID, basically which hotel this room belongs to and if it is available or not. And then we have rate. We will have hotel ID, room type ID, date, and rate. This is, as we discussed in the requirement, based on the availability, we will have different rate for each type of room in different hotels based for different dates. That is why we have kept each hotel ID having different type of room types. At specific date, they will have different type of rates for that. Again, similar thing, rate can be dynamic as we discussed above. So we will have for a certain hotel ID and certain room type on a specific date will have a rate which can dynamically vary. Then we need reservation. This will have reservation ID as its primary key, hotel ID for which the reservation is being made, room type ID and not the room ID as we discussed above. User will be booking a specific type of room and the room ID or the room number we will be allocating to that user once they actually physically check in to that hotel. Start date and end date of that reservation, status, and the user ID making that reservation. Then we would need is a room type inventory. It will have hotel ID, room type ID. This can combination of this can be a and date can be a primary key. Then it will have total available rooms and total reserved, which will help us to know about the inventory, like the total rooms present for that particular hotel ID of that specific room type on a given date, total available rooms, and how many are available and how many are reserved. Similar thing, this gives about each hotel ID for all the room types on a given day, what is the inventory of the rooms. Rooms available now is basic maths, total available minus total rooms that have already been reserved gives us total number of rooms available at present for that specific hotel ID of those specific room types and on a given date. Okay, so coming back to our status of a reservation can be further linked to the payment made or so for that reservation. So we can link the status field to that. Like initially it can be reservation held, then payment success or payment succeeds. So it can be updated to booked. If payment fails, it can be updated to payment failed or payment pending, etc. And say if it passes a given timeout threshold and payment is still not made, then it can be updated to say expired or something. So this all status field can be handled for that specific reservation the user has made. Whatever we have discussed so far, let's see how the high level design would look like for this system. So we will have users and we will have admin. We have API gateway. So it will do all the authentication, rate limiting, etc. All these sort of things. Users will be calling hotel service to browse and know about the hotels that are there in our database and the rooms inventory it has. Then there will be a rate service. This will be handling the rates that are dynamically being adjusted based on the inventory logic on a given date for a specific hotel. Then there would be a reservation service which will help users to make a reservation, edit a reservation, cancel a reservation, and all those sort of things. These microservices will be calling our database to make the reservation, fetch information, fetch rate, and all those sort of things. Hotel inventory can also be stored in a cache so that it can be fetched in a lesser time, and we can have a low latency for that to fetch and the hotel and rooms information, which is not changing that frequently, not the booking information or the rate information I'm talking about, just the hotel browsing, rooms browsing, and that sort of stuff, to cache information about hotels and their rooms, etc., which are not being updated frequently, so they can be stored in the cache as well. Then at the other side, we have admins. So this will be calling from the similar flow, hotel management service, which will be hitting on similar databases to add the hotels, do CRUD on the hotels, CRUD on the rooms, etc. Now let's focus a bit on room inventory. So with room inventory, we did was we kept hotel ID, room type ID, which type of room this is, and where and which hotel it belongs to, and the date. So this we took as a primary key above. We can also discuss on the overbooking use case as well, because hotels generally tend to take overbookings because a lot of users eventually don't show up or make edit to their reservation or eventually cancel their reservations. As we expect users to cancel or update their plans, so generally hotels tend to take up 10% overbooking on specific room types. The reservation can grow a lot, and we are storing all reservations data about all hotels together in a single node, what we saw in our design above. Because a lot of users are making these reservations, so this will easily fill up with all the reservation data, and browsing through these reservations could become a little bit difficult if we are tend to store all this data in a single DB node. To make system scalable and improve latency of it, we can only store current date plus future reservations data. All the past reservations data which have already been done can be moved to a cold storage. We can also implement database sharding, moving each hotel based on its hotel ID to its own shard. As the first filtering layer is a hotel ID itself during the reservations process, it will filter a lot of data. So this is like we are doing querying and fetching information and making reservations, getting details about the reservations, about these hotels from the database. So we don't want our queries to eventually slow down once the database becomes bigger and bigger. So these are a couple of strategies we can discuss and take care of, and like plan to take up to optimize our queries and optimize our flow. Issues which can come up while making reservations. So let's try to focus on that now. We have already discussed on idempotency. We made reservation ID as an idempotent key to avoid double bookings. To avoid double booking by a user over the same checkout details. So let's say a user all finalized on the checkout page. So we created this UUID as the reservation ID. Let's say now the user submits the reservation, call goes towards the reservation service with that particular reservation ID, and some network delay happened. The reservation got submitted and inserted, but due to the network delay, the user didn't receive the response or the act back that the reservation has been made. So after some time, the user submits the reservation again from the same checkout page with the similar reservation ID. So as already we have received this reservation, as we took reservation ID as the primary key, so we can check back in our database that this reservation ID has already been taken care of. So we can revert back with a response to the user. Second issue that can come up is when there is say limited rooms left, say just one room left, and multiple users are trying to book the same room, maybe it's some festive date or something. This is concurrency issue, that multiple users read the same inventory value of one room available of a specific hotel, of a specific room type and specific given date. They all try to make reservation now because they read the same thing, that just one room is available. Transactions are isolated to each other. So all transactions passing through can cause inconsistency on reservations. As all the users read that only one room is available and they made the reservation on that, each user will trigger an isolated transaction, and if not taken care of it properly, these transactions can eventually cause inconsistency and all users ending up booking the same room, even though inventory only had one room available. We need to handle this by implementing locking mechanisms. We can have pessimistic and optimistic locking, and transactions has two parts to it. Firstly, there is check inventory for availability of room, right? Second is, if there is availability of room, then make reservation and update room inventory, right? So there are two flows to this. Let's see with pessimistic locking how we can take care of. It places a lock on the record level when system is trying to update it while making a reservation. So the lock would be made at that specific record level when the reservation is being made by our reservation service. All other transactions wait till the one that acquired the lock fails or commits. So as all the users read the same one room available data, and there is this highly concurrent environment for a very famous festive date for that specific hotel ID and specific room type. So they all triggered the reservation, which eventually triggered isolated transactions. But with pessimistic locking, having a lock at the record level, all other transactions will wait eventually till the one that has gone through and acquired that lock fails or eventually commits. Now, generally, this approach isn't very much scalable, as taking locks on the record level can cause other transactions to wait a lot, causing poor latency. And also, we need to manage and ensure deadlock as well, as there are multiple flows to make a reservation, update room inventory, and those sort of things. So, performance can be impacted and deadlocks can eventually happen with pessimistic locking. We can also have another type of locking as well, which is optimistic locking. It allows all the users to make the reservation, say when one room is left, but only one makes it with success and all other fails immediately, letting users know to retry or out of inventory. So only one goes through and others immediately fail and give back the response to the user that they are now out of inventory for that hotel ID and that specific room type on that given date, what they earlier read as one room available, and maybe ask users to retry, giving out much better UX than pessimistic locking. UX is user experience. Let's see it from a diagram. Let's say we have two users. Now they both read version v1, okay, of that certain record. User 1 early on makes a reservation and writes v2 before the user 2 can make that. So user 1 will update the version for that record as v2, which both earlier read as v1. Then after a certain time has passed, user 2 decides to make the reservation and writes. This will eventually lead to conflict, as what user 2 read as version v1 that has been updated to version v2. So there will be conflict, as v1 has already been updated to some other version by other users within this time frame. So we will ask user to retry, or if it has limited inventory, So it fetches details again and will get back out of stock or out of inventory for that hotel ID, that specific room type on that given date. Further things that can be discussed, say a user makes a reservation, our inventory gets decremented, but on making payment, it fails. So we had a status field, which we discussed above while discussing DB schema, with which we try to treat it as a state machine rather than just a field. So when user made a reservation, it inserted record for that reservation, for that specific hotel ID, room type, that specific start and end date, and it also had a status field as well. So we will treat the status field as a state machine because we are then dependent upon making payment. Typical states that we can discuss are held, as we discussed above as well, which means booking is held before payment. So that can be a default state as soon as reservation comes in. Cancelled, booking has been cancelled. Expired, some time was given to make the payment, but it didn't get triggered and happened to be success by the user, so it would be marked as expired. Then confirmed, booking is confirmed as payment was made within a given time and it got success. Failed, booking got done, payment was tried to be made, but it eventually failed. User reaches checkout with proper details, where idempotency we had on the reservation ID, in place to avoid double booking on same details. We make the booking if inventory is available, decrement the inventory, but update status under held because payment is still pending over here. It's just that the reservation has been made by the user. As I just mentioned and we discussed above, this is temporarily holding the booking, giving user a chance to make a payment till a certain time interval. Now we can expect payment result as success, failed or cancelled. And on the basis of that, we update the status field. So on cancelled and failed, we update the status field by those specific values and also revert back the inventory that we held temporarily. On success, we update status field to confirmed. Inventory during that reservation, if it was available, we already decremented it. So that with payment success, it's all fine. With payment cancelled, failed, expired, and those sort of things, those sort of status, we need to increment back up with the inventory which we just decremented and we held temporarily. If something happens in between, during updation of states, say payment got failed, but we held the inventory temporarily. For this, we can run a scheduler after certain intervals which checks if the status is still held and the expiry TTL that was set is before the time now, so we can update it to expired status. As per Stripe docs, it listens for events from Stripe on your webhook endpoint. So this is what we are discussing and going a little bit deeper with the payment side of things. So it listens for event from Stripe on your webhook endpoint, and your integration can automatically trigger reactions. So Stripe or other payment providers can push real-time event data to our webhook endpoint, which we have integrated whenever event happens at the Stripe side. So whenever there is an event happening related to the payment at the Stripe side, they give us a webhook to integrate within our system, and the event would land up at that webhook, and we can take our required decisions accordingly to update those status field, increment, decrement the inventory, and so on and so forth. Getting these events via a webhook endpoint helps our system respond and take required actions. Example, customer bank confirming a payment, recovering payment succeeds, etc. We can also have a reconciliation job that periodically compares our database payment state with the provider state and fixes the mismatches. Also taking necessary actions if mismatching occurs. It also refunds if user has done duplicate payments for same booking due to maybe network failure, network partitions, etc.